Welcome to Queens College Physics Department's distance learning program. This is our second semester lab program, and this is Lab 7, Capacitance. We're going to be looking at the concept of capacitance, what it means in general, and for the static case, and in a circuit. You've probably learned something about capacitance already. Capacitors are, after resistors, are one of the most used components in electronics, and you can read about it anywhere. As you learned with DC circuits, resistors or a network of resistors can be combined into a single resistor. The same is true for capacitance, though the rules are swapped around a little bit. Something you can read about in the introduction and just about anywhere on the internet. The resources for this lab are the document, which you're seeing on the screen, the demonstration video, which you are now watching, a capstone file, which can be downloaded from the Blackboard assignment, and we're going to be using the FET circuit construction kit again. In this case, it's a slightly different version. It's a prototype. It has some hiccups and performance problems, but in general it works much like the other one does. This one, though, is geared for AC, and it includes capacitors. And you can read about the subject anywhere. Your textbook, any number of sources on the internet. Presumably by now you've studied it in your lecture course. You can read the introduction on your own time. I'm going to go to the procedure 1 apparatus now. And here we have the apparatus we're going to use. This is a parallel plate capacitor setup from pasco.com. You can go to that website and look up the device to see how it works. We're going to be using it in a very simple way. At the very back is an electrostatic voltage source, and I've got it connected to 30 volts on this lead, which I'm trying to leave off to the side. I have an electrometer in the position between, which is connected to the plates. The plates are isolated, means they're not connected in any way, and I have them separated at 5 millimeters. They're connected to the electrometer. This side is the ground, this side is the lead, the positive lead. I'm going to charge this side, and then I'm going to separate them in regular increments, and then I'll show you how to use that data. Now there's a problem here, and there's always a problem with electrostatics. It's very hard to get precise readings. As you can see just sitting here, that my electrometer is not zeroed. It says 3 volts. If I reach over here and press 0, I can get it to 0. However, you'll see when I turn on capstone that things are not that simple. And let me introduce capstone now. Here I have a capstone file. I've set it up with the electrometer on channel A, which is the setup I have. I'm reading the voltage as it changes in time. And all I have to do is press record. And that's it. So you've seen this before. So now let me get prepared for procedure 1. So I'm going to press record. And I'm fairly close to 0. If I move my hand in here, you'll see that I'm not close to 0 just because I'm close. I will try to get it back to 0 by many ways, and I'm unable to do so. Such is the nature of electrostatics. It won't matter to our results. I'm going to take my lead. I'm going to touch that plate. It's going to shoot up to approximately 30 volts, which is what I have it. And that's your first plateau at 5 millimeters. The next one is at 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. And I'm going to stop there because you're already not seeing any response. And stop. And that's what we're going to use that setup for this time. Now let's go back and look at the data. And here's the data I've just collected. Doesn't look like much at the moment, but we're not interested in most of it. We're interested only in this. And if I do this, I can increase the resolution that way, and even more. There, not bad. It is what it is. Okay, so where I need that first plot, right, at 30. So here's my first plateau. That's 5 millimeters. I then separated it to 10 millimeters and left it there for a second, and then 15 and 20 and 25, 30, 35, 40, 45, etc. I want you to find the mean of those plateaus. We're going to use a box, which we're going to make narrow, and we're going to grab it and we're going to go down here. So it doesn't have to be narrow here because it was there for quite some time. I'm going to take that and avoid the little nonsense, and the mean is 29.5. If I close it up, you see that it changes very little. That's a little narrow. So now that's 5 millimeters, and if you take it up and place it there, you'll get 10 millimeters and 15 millimeters and etc, etc, etc. It gets a little hairy up here, 37.7, 37.8, 37.9, 38.1, 38.1. You'll record those anyway. I did from 5 millimeters all the way through to 8 millimeters, 80 millimeters, and that should be 8 different plateaus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It should be 16 plateaus. You're not going to get 16 plateaus. It's getting a little hairy up there, but if you play around with the scale, you'll be able to get 14 or 15 of them. You're going to prepare a table in Excel with the separation distance, 5, 10, blah, blah, blah. You'll have to change that to meters to make the units make sense. And then you're going to input the voltage that you measure from this data. And then you're going to plot it in Excel using a scatter graph. No weird line graphs, points only. We add lines using the trend line. You can read how to analyze this once you've gotten that data in the Google Doc. And that's it for the first procedure. Now we're going to look at something else. All right, so let's look at procedure 2. Currently in our apparatus, the air between the two plates is filled with air, which is a kappa, a dielectric constant, of approximately 1, the same as the vacuum for all intents and purposes. I have a charge on the plates. Plates are separated by 10 centimeters. And I now hit record. And you see that I have a constantish charge with a mean value of 27.6 across the plates. I now insert the paper. This is a box filled with paper. It's dry, though there is ink on the paper, around the paper, etc., etc. And then I'll pull it out. And I go back to my original value. So let's stop that. And now let's take a look at the data. And here we are. So let me spread that out a little bit. And you can see it because I gradually slid it in, the dielectric constant in that space increased. I slid it out a little bit faster. A little bit of nonsense going here. We're just going to, this is very approximate. These kind of measurements are very hard to take. I'm going to make this smaller. And I'm going to take, what am I going to take? It should have come back to the same value. If I ignore all the little nonsense, that value appears to be about 27.6. I think it was 27 point, what did it start as? 27.5. So 27.5, we'll take that. 27.5. Now, what went on here is unclear, but let's just take this from 27.5 to 23.6. And those are the values you'll use in the analysis. They're very approximate, but then so is this whole procedure. You can move to the next procedure now. Okay, welcome to procedure 1.5. It's 1.5 because I had originally planned it differently, but I want to insert this one before the other ones. I think it's helpful that way. So, procedure 1.5. We need the construction kit for this. And you get there through the link. When this oops, you get 3 choices. You'll choose lab. And it looks pretty much like it used to, but there are a few extra features here. I prefer circuit diagrams. We don't need current here because it doesn't make any difference, but the values probably don't make much difference either, but it's enough for this. There is an extra control here. This controls time. You have 2 choices. You can let time run, which is what's happening now, or you can turn time off. This other button just allows you to move at set increments. I'm not going to be using that. But I do want time off now, so I can build my circuit in peace. So I need a battery, and I want a resistor. I need a resistor here, well, for reasons you'll see. But I want it to be slightly more modest. I'm going to go down to 3 ohms. And I want to switch because it's going to make my life easier. And of course, I need a capacitor, since that's the whole point here. And I'm going to wire it up. Now, this is an open circuit. While the battery can provide 9 volts, it's not going anywhere. So the voltage across this capacitor is going to be 0 volts. As it should be. And let's get a current meter in here as well. This is a different kind of current meter. The ones you're used to seeing are the ones with 2 probes, and the current passes through the meter, and that's how it's measured. But there's another way. You can take a wire with a current in it, you can put a ring around that wire, and it will detect the magnetic field of that wire. And then the meter calculates the current from the magnetic field that it detects. And here it's saying question mark because it's not happy. There we go, 0. No current flowing, but of course it's an open circuit. So let's run time now. So time is running and nothing is happening because it's still an open circuit. Let's close the switch. Watch the voltage. If this was a resistor, in which you saw in previous labs, this would jump to 9 volts. And this would not go down to 0. It would remain at the current of Ohm's law gives you 3 amps. But that's not what's happened. Something is different here, and it's because of the capacitor. Let's open this switch again. Now, the current should be 0, because there's nothing else happening here. But if this had been a resistor, this voltage would have gone to 0 as well, and it did not. In fact, I can actually disconnect it and reset my probes, and it's still 9 volts. What's happened here is we've charged the capacitor, and we've given it no way to discharge, so it retains that charge. If it doesn't leak. Real life, they leak a lot. Here, we have an ideal situation, no leakage. But we do need a way to change that. We need to be able to discharge the capacitor. You can click on it and you can press a little lightning bolt and discharge it, and now it's 0 volts. So we saw that this takes time, which is why we have a time control over here. Let's put this together again, and I missed here. And this time let's get a chart, a graph, which we can measure the change in voltage over time. This says 0 volts. We can do one for current too. I want to line them up. You'll see why in a minute. This is again one of the type of amp meters that works by a loop or a ring, and we're good to go. So now if I close the circuit, the current, you're not set, right? There we go. The current here is 3 amps, and you can see that this has jumped probably to 3 amps. That's what the current is. And the voltage here is still 0, and it still says 0. So what happens now when I start time? Well, wait a second. Let's go one step further. Let's introduce a stopwatch. And I've got it set to go. It'll go when time goes. And I'm going to watch the voltage change, and when it hits a peak of 9 volts, I'm going to stop it. I'm attempting to time it here. Bad attempt because I'm using my reflexes to do it, but it'll do. And off it goes. You see it goes up, and it's 9. And that says 2.68 seconds. Probably it's a little less than that. And you can see what's happened here. The current has gone from the 3 volts when the capacitor is uncharged. And an uncharged capacitor is acting like a wire. It's like a short circuit because any charge coming on this side pushes charge out this way. So it's an open circuit, so the current jumps to 3 amps. And charge starts to accumulate, so the voltage jumps. And because the current's high, the change in voltage is fast. As a charge accumulates, it can only, it gets repulsed a little bit, so it doesn't accumulate as fast. So it slows down until it hits a peak of 9 volts, and it stays there. Once it's charged, it has its maximum charge, it can't do anything else, it stays there, and now the current is 0 because no more current can flow. So Once it's charged, the capacitor acts like an open circuit, in a DC circuit at least. How long that takes, here we have 2.68 seconds, depends on the value of the capacitance and the resistance in the circuit. I'm not sure who programmed this, but I don't have enough confidence in it to actually do a lab where you can make calculations. But you should calculate the time constant, the RC time constant. I say that specifically because you'll have to just do a Google search to find out what RC time constant, how to calculate it. It's very simple, don't worry, and calculate it. And I guess that's all we can do here. So another question you can answer, and will appear in the lab, is that for a DC circuit, the long-term behavior of a capacitor is as an open circuit. It cuts off the flow. But what about an AC voltage, an alternating voltage? Will it have the same behavior? So your job, whether you accept it or not, is to replace that 9-volt battery with an AC voltage. Set it up and run it as I did, and see what the response is of the capacitor is in an RC circuit to a alternating current. And take a screenshot of that and put it in your report. And that's it for procedure 1.5. Before we start with the circuits in the procedures, you're going to need to know the values of the capacitances of C1 through C4. I've aligned them here. This is C1, C2, C3, C4. You can read this display here. The decimal point is 1 to the, well, you can see the decimal point. And it's set to read in the range of microfarads. So if I put my probes here, I get 2.0 microfarads, and you can read them. .1 microfarads. 4.4. And 6.8. So make sure to record those in a table somewhere. You're going to need them for the rest of the circuits, which I'm going to set up now. Okay, the next procedure is for a series circuit. I can't measure capacitance when there's a charge on the capacitors, so I'm omitting the power supply. And I'm going to just chain the capacitors together to make it a series circuit. So I'm running from this capacitor, C1, to C2, C2 to C3, from C3 to C4. And now if I use my probes, I'll put one here in C1. And if I stick my probe in here, overload condition because I have the range changed. There we go. And if I put my probe in here, we're going to get our 2.0. If I bring my probe to here, I'm going to get 1.1. If I bring it to here, this is C1, C2, C3 together, I get 0.9. And now that I've gone down that far, I'm going to go up to the next range. And now if I put my probe here, I get a capacitance of 0.868 microfarads. And that's your job for this procedure. You're going to use the formulas and the values that I measured earlier, and you're going to calculate what the series circuit capacitance should be, C1, C2, C3, C4 in a series circuit. This is the measurement. Your calculation should, of course, be close. Okay, here we go. We're going to do the next circuit, which is the parallel. Again, I don't need a power supply. What I have to do is connect these in parallel. So these devices are set up in such a way that this is just a piece of wire which is connected to this side. This is the capacitor which is connected to this side, and these two legs are joined together. So if I want, I can connect here, and if I measure that, it will be the capacitance. In fact, I can do that. And you see it's the capacitance of the capacitor. If I want this to be in parallel, then I need all of these to be connected together. And I can do that like this. So these, well, there's many wires here. It is a junction connecting all of the one side of the capacitors together. And of course I have to do the same thing on the opposite side. And there we have it. We have all of the connections on either side of the capacitors connecting all together with a junction on each side. So that is C1, C2, C3, C4 in parallel. The lab asks you to measure the parallel capacitance, the total capacitance, which I will do like so. And I get a capacitance of 16.6 microfarads. Your job is the same as with the series circuit. You're going to use the formulas and the values that I measured for the individual capacitors, and you're going to calculate the total capacitance, which should, of course, be close to this. And now let me set up the final one. And now we have the combination circuit. If you have a circuit diagram, you have C1 in a loop with C2, and C2 is in a loop with C3. Remember, I said he's used to build these circuits in loops. So I have to connect C1 and C2. I'll connect them this way using the meters. I'll be replacing the voltage sign in the circuit diagram with the meter. It's the easiest way to see this. So now I need a loop between C2 and C3 to make them parallel. So I join both legs together. And now I can measure the capacitance by going from there to here. If I can get all the little wires out of the way, you get 1.5 microfarads. And that's it for this part. The only thing left now is to do the analysis.